but noon on Tuesday is like the last time I can possibly get it onto my laptop in time for the videos on session, which will be in the lecture time on Tuesday. Just to make sure I've said it again here, but you get to choose whether you make your video on YouTube public or unlisted. If it's private, I won't be able to see it, but if you make it unlisted, then it's almost private. When we're in here playing the videos, we'll play all the public videos first, and we'll go ahead and let the stream run and let people watch, and I'll have slides.com so they can follow along with it going to their browser. And then time permitting, we'll go through the unlisted ones too, but actually we might run out of time. So I think we're going to go, we've actually got this room until 5 o'clock. So we can stay a little bit longer, but at some point even though the videos feel incredibly short for all the work you've done, it's going to take a time to go through them. So we'll go through as many as we possibly can, hopefully all the public ones, and start going through the unlisted ones after that. A few other questions that I've heard people ask lately. The write-up, just to say, is officially by institute policy, we cannot make an official deadline for the write-up past Tuesday. So that I can't move that officially. So that's staying. That hasn't changed. A few people asked about, if I've deviated from my original proposal, is that okay? Do I have to update the proposal? And the answer is no. We're evaluating the final report based on the work you did for the final report. The proposal was for us to get you started thinking about it and to give you feedback. It was not a binding contract. You don't have to update if you've deviated. That's all good. Hopefully you kept us in the loop a little bit if you deviated a lot, but that's fine. Okay, yeah. I mean, we hope that you don't actually make your video at 11:59 on Tuesday morning, because the whole point was to give you a little bit of a gap so you can actually finish the video and then work on your write-up, but you get to pick. Okay, so today we're going to talk about feedback motion planning, which I feel is one of the last big ideas that I really want to make sure we land. I think it'll connect a few of the things we've been talking about over the course of the term together. I mean, if you think about all these different ideas that we've talked about for control and planning and the like, I mean, there is sort of, I feel I've presented it as if there's a bit of an artificial dichotomy, I guess, between, there's a bunch of algorithms that try to come up with feedback controllers, right, with policies, if you will. And then we have a lot of different algorithms that are doing trajectory planning. So let's just start, just make sure we kind of think a little bit about, is there any real difference between a plan versus a policy? Is that just semantics, or is there more to it than that? Right. Certainly, we've seen examples of places where that line is blurred, right? So, for instance, MPC, model predictive control, was an example where if you have a planner that's fast enough, then you make a plan. You take the first action, then you make another plan. And that's a way to turn a plan into a policy. And I'll go through a few of those sort of those connections here right now. But I do think there's a bit of a fundamental difference between having, an explicit, I think of a policy, especially one that's sort of explicit. If an explicit function, u equals pi of x, for instance, or like we said last time, even if it's an explicit parameterization of the dynamical system, versus an implicit representation, which would be, u is the result of some computation, let's say. potentially some plan or some more extensive computation. Right? Why do I think those are sort of meaningfully, that distinction is meaningful, right? So in some sense, I think an implication here is that if you're going to do pi of x as some explicit function, even if it's a neural network, a feed-forward neural network would be an explicit representation of a policy, as opposed to something that's using a model and planning on the fly. Then there's some sense in which you've had to think about or design, optimize, consider all possible x's that are going to be in your operating condition before you evaluate pi. Right? And so there's a lot of great things that come from that. You can talk about the robustness of a policy. You can do lots of things, okay? But there is some implication there that you've pre-solved for pi. And pre-solving for a pi for all possible x seems like a hard thing to scale to very large state spaces. Now, you can pre-solve for pi for just the relevant x's, and that's a useful concept, okay? But planning, I think, does fundamentally scale better, okay, right? Where in the extreme, you can have a plan that just considers the current state, doesn't have to worry about all possible x's, and just reasons into the future. Okay, no, this is the kind of philosophical debate that you have over drinks if you're, when the robotics seminar speakers come to town, and people talk about plans versus policies, and really, what do you think? And but let me just do my take on it, right? So, if I think about like what does my walking controller look like for some sort of steady state gate? Sorry, I'm gonna make it hard for you to track me for a second. Sorry, right? I probably have some explicit map somewhere in my nervous system, right? Feels more like a policy to me of like the things that I'm doing often. I've probably baked in some control gains that are almost reflexes, right? That are probably feel very much like a feedback policy, right? But there's other things I do in life that I think feel fundamentally like a plan, right? So let's say you're going to book your summer vacation, right? And you're going to some exotic place you've never been before, right? You probably don't have an explicit policy of like everything you would do to, get to Tahiti, right? Like you're probably going to do that once and just reason about the steps that would be required to get to the airport and get to whatever. And that's something maybe you'll never do again, and you did exactly once. And if there was another place, you would have to reason it out again, right? So there are some very like high-level tasks that I think people disagree with me on this, right? But I think feel like I'm doing online composition of online reasoning in order to make my decisions, okay? So the interesting question, do you agree with that? Is that sort of like those two extremes, for me, they seem sort of okay. The interesting part is in the middle, right? So how far do I get with legged locomotion as a feedback policy that's been pre-computed, versus do I do planning on the fly for legged locomotion? So Marco, for instance, Marco Hutter, when he was here and talking about Animal, the one that's walking all over, he was really arguing that I can just do everything with a feedback policy, that I want to train a neural network well enough, and he's like, nothing that I can't do is roughly his stance with a policy, that legged locomotion is a policy. Even navigation, he wanted to go way up the stack, saying like, everything's just a feedback policy, right? But I don't know, maybe, like, if I'm, think about the extreme cases, right? Like if I'm, up against some novel obstacle course, right? And I really have never seen that before, and I'm never going to see it again. Do I really have that pre-computed for every possible obstacle course? Maybe there's a representation that makes that okay. Like if you're looking at the Ninja Warrior, we watch like Ninja Warrior with my kids, right? So, you kind of see people like, you can almost see them planning, right? You can think like, I'm going to do that, and I'm going to do that. Little mental visualizations, going to get them through the course, right? There's got to be like cases where I do reason about, okay, this is the first time I'm going to do this. Or if any of you are climbers, right? Like I think climbing is like a beautiful exercise where you're kind of like, I'm going to do this route, I'm going to do this route, it's going to be different, I'm going to hit this, I'm going to hit this. So those feel like places where we do have the ability to do online planning and reasoning, in my opinion. It's good. It's a good conversation for drinks, like I said. So I think this interface between planning and control is a very interesting one and a very subtle one. So I think the ability to do online something you've never done before, never seen before, never considered before, feels important to me. But I also feel that the way we've talked about planning so far is somewhat limited, where we think about trajectories. It's like either I've got a big feedback controller or I've got trajectories. And I want to break down that barrier. It doesn't have to be either or in such a clear way. There are nice ways to combine the two. And that's my goal for today, is to tell you about at least one of them in some detail about this idea of feedback motion planning. So let's just think about a couple of the cute ways we sort of have seen or almost seen, or I can tell you very easily about the ways that you could blend these two worlds. Okay. Let's say you wanted to go from plans to policies. And again, I'm using those a little too simply, but I really mean it's almost, explicit, implicit kind of things here, okay? So we've seen, model predictive control is a great example. Make a plan, take the first action, throw it out. That's certainly one way to take a planner and use it like a policy. There are other important ways. In the sample-based motion planning world, for instance, in RRT, especially RRT star, I think is even more so like this, backwards from the goal. You could think of starts to trend towards a policy. I can make that graphically clear, I think, and courtesy of Sertaç's videos. But you remember the RRT, that was the randomized trees. This was an example of making an RRT from the start, trying to branch out and eventually find a path to the goal, with probability 1 as the number of samples goes to infinity. Okay. But if you look at the structure that's happening here, I have this expansive tree that slowly covered a lot of the state space. And if you think about it sort of from the other perspective of here's my goal, okay, here's my goal, and I build it out. In RRT star, we didn't talk much about, but it does a little bit of rewiring to try to find, it has a cost function now, so it's an optimizing version of the RRT, and it tries to remove branches that were inefficient and shortcut them to branches that are more efficient. And by the time you fill out this tree, you really have sort of made a policy, right? You have all these branches that are going towards the goal from an expansive coverage of state space, okay? So that's a way to sort of get policies out of a planner. There are others, there's an idea called guided policy search, which sort of falls in this world where if you just run a planner lots of times and then, for instance, train a neural network to store the output of your plans, then there are many ways to do this, but that's one name for it these days, is to sort of use many plans as the target to learn a control function, right? It's a way to do take an implicit representation into an explicit one. There's also things called Explicit Mpc, which try to explicitly represent as a function the solution that you would get out of a model predictive control for every possible state. Okay? So there are lots of ideas that would sort of take the machinery of planning and try to turn them into an explicit representation for all states. And those are good to to know about. It's sort of interesting to think about it the other way, too. If you have a policy and you want to do planning, that sounds like a silly thing to say, right? But we've seen a couple examples. We've seen at least one example of it, right? So the motion primitives, I almost wrote Emilio's thesis. I guess that's almost as good, right? I'll just write it. Do you remember this idea that if you can solve the value iteration policy for the helicopter when there's no obstacles, then you can use that to guide the search of your randomized planner when there were obstacles. Right? So that's a way to take a policy that's not perfect, didn't have all the information, but then you used it online to do more efficient planning. And actually, we didn't talk about AlphaGo or AlphaZero, but AlphaZero is doing roughly that too. If you've taken any time to read, the way that AlphaZero works, it has a plan that it's a policy that it's learning, and then on every step it does rollouts guided by that policy, right? That's the same kind of thing as Emilio's thesis, right? It uses the approximately optimal policy to guide the search to do better, effectively have a deeper kind of rollouts, and then it uses those plans. It sort of does the guided policy search, or sort of, it uses those plans to refine the policy. So that's a beautiful way to sort of combine the two worlds of these online planning and tuning up a policy. But there's another big one that I think we haven't, you might not come up with unless you hear about it, and that's the sort of feedback motion planning. And I'm going to dig into that today. But the basic idea is I'm going to plan to run a controller. Okay, I'm going to plan a composition. Like, I'll run this controller for a little while, and then I'll run this controller for a little while, and I'll run this controller. I'll have a toolbox of controllers, possibly parameterized controllers, and I'll decide to compose my controllers into a more complicated sequence than I had previously computed, get some of the benefits of feedback control, robustness, and the like, but have some of the compositionality and novelty, extending to novel scenes and stuff that you can get out of a planning kind of framework. Okay. It's my last chance to sort of give you some of the fun, simple examples of beautiful dynamics and control. So I'll give you one more model system, and it's the model system that inspired the paper, that inspired me to think more about feedback motion planning. So it's not arbitrary here, but so a little case study, if you will. Robot juggling. Okay, so there's a great series of papers by Dan Kodacek and his students, and have gone on to be very independently successful, series of people and of papers that studied robots that could juggle, right? Now, juggling can be a fancy thing, right? I could start with a fully dexterous hand and, I don't know, like a flaming torch, but we're going to start with a simple model. That's, if there's one thing I want you to walk away from this class with, is think about the problem you're interested in, write down the simplest model that captures that, okay? So the simplest model of juggling is actually extraordinarily simple. You can have basically a paddle, okay, and a ball, and you can even constrain the ball initially to move only in the y-axis or the z-axis, if you like, okay? Don't even worry about it falling down this way. Let's just start with it perfectly. And similarly, this paddle can only move up and down. And our first goal is to we'll model the elastic collisions of the ball and the paddle. And we'll try to come up with a policy that drives the paddle up and down with respect to the state of the paddle and the ball in order to stabilize a certain hopping height, okay? So that this is actually done, this was one of the models that people used to think about hopping robots too, that Dan claims to have been inspired in his juggling work by Raybert's hopping machines, okay? So this is a beautiful system. It can be parameterized simply with the height of the ball from some nominal zero and the height of the paddle, if you will. We'll say that the state of this system you can write down as basically the ball height, the position, the paddle position, the ball velocity, and we'll just assume we can directly control the paddle's vertical velocity. And then we assume that it's perfectly elastic, impulsive collisions. We do all the stuff that we've done with our walking robots. Okay. Then you say, how could I could use trajectory optimization. I could do dynamic programming. There's a lot of different ways you could think about trying to design the controller with our tools from class. But it turns out Dan and Martin Buehler and his students came up with a very elegant class of controllers that make the problem extremely simple. So, and that class of controllers are called the mirror laws. Where they would choose policies of the form so R equals negative KB roughly. Let me just write it like that. Okay, so I'll even let me write it as the position of the paddle is just a mirror of the ball, okay, with possibly some gain. Right? You don't need to be exactly like this, right? So I could take this situation where the ball and the paddle are together at the 0, 0 position, okay? Now the ball moves up, and I'm going to say, I'm just going to track the ball, and whatever the ball does, I'm going to do the exact opposite in some scale. Now that's beautiful for a number of reasons. First of all, it simplifies a lot of the equations because you always have collisions exactly at the origin, just by design, okay? So it turns out you can drop some state variables and do a beautiful Poincare analysis on the bounce-to-bounce map, where you know the impact always happens at R equals B equals 0, right? So those just go away, and you can write a return map as a function of B dot, from B dot from one height to B dot to the next height. Or you can do it in terms of the apex, but it all works out. You'll see beautiful, in these papers, you'll see beautiful Poincare maps that have an unstable fixed point at 0, 0, a stable fixed point at the hopping height, right? It's all the stuff we know. And through that series of control analysis, I mean, you can put fancier terms in here if you like, but you can say, you can build beautiful feedback controllers that sort of work in practice. And then, when you want to do fancier juggling, I mean, I don't know, I don't do juggling tricks, but you could sort of imagine maybe flaming something, sharp knives, maybe all of the above. Okay, you've done some hard work and some deep thinking about how to make this feedback controller. You don't want to throw that out and just start planning trajectories. You got a good controller here, right? So, and you can extend this controller, right? So in the 2D case, now I've got like a paddle that's going to move in theta. It's like a pinball thing. Okay, the ball's moving here, but now the ball has, let's say, the x, z condition, and the paddle is just still 1 degree of freedom, but now it has to stabilize itself both in, x and z, okay? It turns out that almost exactly the same controller works. If I do a mirror law on this, I'll still connect exactly at the origin. But if I add just a small term that stabilizes, bx, then you can have the property that basically if I'm let me see if I get this right. If I'm too far this way, then I want to be a little bit shallow when I hit, so that the ball will go back that way. If I'm too far this way, I want to hit a little bit past the horizontal. And a very simple correction, you just add like sort of one more term here on bx, and you get a mirror law that will stabilize yourself in x and z. Beautiful. And then you can do things like, oh, what if I have multiple balls, right? That's, of course, in fact, one of the students that worked on this was like a real juggler. He could juggle, I don't know, 19 balls or something. And so not a surprise that they quickly did more than one ball. This is one of the early ones, right? So imagine just doing that, running that controller on 2 balls simultaneously. It'll take turns now deciding when each ball is coming close, which one to mirror. And you get like beautiful, robust stability, both in X and in Z. Again, this is a beautiful, in terms of experiments now, if your eye is keen, you'll realize that's actually on an air hockey table that's tilted up at an angle, right? So that's how they got rid of that extra plane, right? They didn't have to worry about the ball falling out sideways. It's just a hockey puck, or air hockey table. Okay. And of course, then they wanted to get more fancy, so they started doing things like in 3D. They could do palming, catching, these same sort of like different choices of the mirror law or variants on the mirror law could give them a bunch of interesting feedback controllers. Okay? And then the question was, now you have like, oh, please, yeah.
How did they track the ball?
So this was, back in the day, so it was typically a white ball on a black background or a bright yellow ball on a blue background. So it was vision-based, I believe, but it was very simple vision-based. Yeah, almost always simple backgrounds and the like. Okay, so you've got a repertoire of juggling skills. And now you're going to put on a show and impress your friends. You don't want to, like I said, you don't want to just throw away all those hard-earned feedback controllers that are nice and robust and stable. How do you compose them together? Okay, and this is, I forget what they're going to drop in 2 balls here, right? I forgot to, there's a bunch of different things that this little 3D juggler could do. Right? So it's stabilizing out of plane also, right? It's got a little bit of this and then a little bit of this. This is just a 3D version. Okay, so in thinking through that problem, I've got these great feedback controllers. How do I put them together? They wrote this paper that I found very influential in my thinking. It was Sequential Composition of Dynamically Dexterous Robot Behaviors. Okay, and the figure caption says, think of a Lyapunov function as a funnel. I guess I like that, right? An idealized graph of a positive definite function over its state space. Okay, so in particular, maybe you could think about the initiation set of that funnel, right, as being the region of attraction, and the action that you'd expect in state space as you run the controller is to take a large range of initial conditions and bring them down into a smaller range of initial conditions. Okay. And then this is the great picture. Okay, so they say, imagine we're trying to come up with a really complicated. We want to stabilize from all kinds of initial conditions, right? And maybe our funnel that we're trying to design should look like that. But we don't have that yet. We have these little simpler skills and feedback controllers. How can we build that more complicated feedback controller? And they said, well, okay, if I have this vision of a controller as a funnel, then I can compose multiple controllers as long as the output of one funnel lands in the input of a next funnel. Then I can think about sequential composition of multiple feedback controllers. And the beautiful idea here, this one's like, oh, that just feels really right, to me, was like, okay, I can potentially build a whole complicated funnel. If my goal is to have this abstract notion of a complicated funnel or put on a juggling show or whatever, that maybe that's just a composition of many, many, many different feedback controllers that can build a more global feedback controller. Okay, that idea seems natural, right? So that was a paper by Rob Burridge and Al Rizzi and Dan Kodacek. Actually, Al Rizzi, who's the one who did the 3D juggling and the like, he is one of the main people working on Spot, for instance, at Boston Dynamics. And Boston Dynamics talks about the locomotion controllers on Spot very much in this language. They say, okay, I've got a good controller we worked hard on for steady state walking. I've got another one for trotting, you know, and then the way we think about sequencing them together is potentially through funnels. Okay, this is funnel-like thinking, right? Now back when this paper was done, they didn't have like sums of squares, right? So they had to do sampling, and they made very approximate, you know, they just drew like an ellipse around the samples that they collected from extensive experiments. You know, but nowadays we have more computational tools, and I think we can think about this differently. It's interesting, you know, this notion of a funnel. Dan Kodacek, when he talks about it, he says, "Oh, we got this idea from Matt Mason." And Matt Mason did have this very influential paper with Tomás Lozano Perez about thinking about, it was actually about peg and hole was the first time they called it the LMT paper, which is, if you've, you might hear people talking about the Lozano, Perez, Mason, and Taylor paper, but LMT. This was one of the early manipulation papers that had this idea of maybe you can plan complex motions by thinking about the pre-image of each motion, kind of like a funnel. This was much more about a kinematic task, and Dan's was much more dynamic. But he says, "Oh, we really got the idea from Matt Mason." And then Matt Mason says, "Oh, I got the idea from Mark Rayburn." And then Mark never gave me a good answer when I asked him. But I do think people were more generous with academic credit back then, right? Everybody's like, no, that was, someone else had this great idea. I think it's a great idea, and it's been used a lot. Okay, so, you know, natural proposal, given the tools from class. What if we have a model? We use sums of squares to come up with the funnels. We have some ideas from motion planning. How would you put all that stuff together in order to make that sort of complicated funnel out of many little funnels, right? And here's roughly the proposal on what it would look like with just the pendulum, okay? So imagine you have this is the pi 0 unstable fixed point here. And imagine I have, you know, I use LQR to stabilize. Are we all good? Yeah? Oh, okay. It's possible it did, yeah. Dead battery. No, it even says dead battery in Word text. Cool, thank you.
Yep, no problem.
Okay, unstable fixed point. I'll use LQR to stabilize the fixed point. I'll use sums of squares to estimate the region of attraction to that fixed point. Okay, now I'll just be back and forth a little bit here, sorry. Okay, now how do if I want to grow this to cover much more of the state space, what can we do? Well, here's a proposal. I've got the stable fixed point at the bottom. We know we can do trajectory optimization to swing up to the top. Okay, and this is what we've done so far. So let's do trajectory optimization to swing up to the top. We know how to stabilize that trajectory. We have LQR. Time-varying LQR can stabilize the trajectory, the finite horizon. We know how to compute funnels around that trajectory. So if you have a terminal condition on the sums of squares along the trajectory to say that the output of my funnel wants to be as big as possible such that it's in the inlet of the next funnel, that puts a boundary condition on the sums of squares, and it'll grow the boundary out. And you can say, what's the biggest funnel? You know, I'm going to push out on the volume of the funnel such that it satisfies the dynamics and lands inside the next funnel. That all fits with our framework. And I made a nice animation about it. Okay, that's kind of what it looks like. The funnel over time. That was the extra axis was time. Okay, and then you can imagine now doing the Kodacek and Rizzi thing where I'll just make this into an algorithm. So I'll combine it with sample-based planning. So I'll pick a point at random. I'll start by stabilizing the fixed point. Now let's pick a point at random. If it's already inside some funnel, I can throw it away. If it's outside the funnel, then that's a state that I have not yet got a controller that describes. So I'll make a new trajectory optimization that goes from there, let's say back to the goal, and I'll add the funnel. Okay, but then I can just repeat that process. Make a new sample, try to connect with trajectory optimization from that sample back to the tree. I've got a tree now, but it's a much sparser tree than the feedback trees we were talking about, just a handful of them, of trajectories that are all eventually getting to the goal. But every time I add one, I'll add the funnel. and I'll slowly chop away at the state space, right? And eventually, there's nice properties that this has, the same way that the probabilistic sample-based motion planning would say that it can find a path if it exists as the number of samples goes to infinity. This algorithm has something we call probabilistic feedback coverage. Okay, so what does that mean? So this was a contrived nonlinear dynamical system, which we designed specifically to know that the states above the red line were not, you could not reach the goal. This is the goal here. You could not reach the goal from here. It was impossible, given the torque limits, given the initial conditions, given the dynamics, to get from this side to this side. So we know that by construction, the region of attraction, the biggest possible region of attraction of any controller is on this side of the state space. And then we said we don't want to necessarily cover every possible state, but I want to sample only in that blue region, and I want to cover as much of the blue region as possible with a feedback controller. And what it does is, even though, so there's a true boundary of a region of attraction, which is complicated, but I mean, it's simple in this projection, but it's complicated to fill out with ellipses. And it will eventually, with probability 1, if there's an area for which it's reachable, it can get back to the goal. It will eventually sample that with some conditions and assumptions on the way you do the connection. You can say that you'll eventually connect. And then you'll eventually, since the LQR controller will, in that stabilizable region, will have non-zero volume, you'll eventually get an ellipse that will take out at least some measure of that space. And in the limit, it will cover all of state space. So if you run this long enough, the reachable, all the states that can get to the goal will get to the goal. And we'll get to the goal with the sums of squares guarantee, right? So that algorithm, called LQR trees, when it first came out, was this idea of trying to combine LQR with trees. Now I hope, given all the things we've talked about, let me just, that you see that it's bigger than, it's not about LQR really. That was just, there was enough complexity that we only did LQR in the initial version of this, but you could do robust control in there, you could do stochastic control, you could do output feedback even in there, although we haven't done that yet. That's been on the list for a while. It's super important, I think. Okay, but yeah, so there's many different ways you could do that. Sums of squares is one way to do the verification. Even that's not essential. I think the essential idea is just to compose the sequential composition of the funnels, a rigorous verification with the sample-based planning. Sorry.
Sorry, why are you sampling on the other side of the constraint?
So imagine, okay, let's say I have actuator, I'm a humanoid, I've got actuator limits or whatever, and I've got some ability to sort of stabilize a fixed point. There's some boundary of that I just cannot stabilize. But typically I don't know where that boundary is, where that real boundary is. We made an artificial problem where we knew, just to show that it would grow. But in general, you don't know what is the largest possible set of stabilizable points. This will discover it for you, potentially inefficiently, by eventually going up and filling itself up against the boundaries. Good question. Yeah?
Just to make sure that I understand, like the
Yeah.
final execution will look like we estimate the state of the system, we look up the funnel which contains the state, and then run the explicit controller for some time.
Awesome. So yeah, so I'll say it back so the video can hear. But yeah, so to execute the policy, then you in the full state feedback case, which is the only case we've studied carefully so far, but you would estimate the state. You would find any one of the funnels that you're inside. In some sense, you can prioritize the funnels that are closer to the goal. So you can put an ordering on there, but you have a guarantee as long as you're in any one of the funnels, you could execute that. Now, there is one state in the controller, which is that once you start executing a funnel, you continue to execute that until you transition out into the next funnel, just to avoid chattering and other things. You don't want to constantly change your mind about which funnel you're executing. But yes, you basically have a small computational geometry problem of trying to find which ellipse you're inside, which is an interesting one in higher dimensions. Okay, but yeah, you find out which ellipse, and then you write it in and have a path to the goal.
So in some sense, this is pre-computed MPC.
This is a, well, so, good, so it says, is this pre-computed MPC? Explicit MPC is exactly pre-computed MPC. This is not quite, I would not quite call it pre-computed MPC in the sense that it's not optimal from every state. It's feasible from every state. If you're using nonlinear trajectory optimization, you have some sense of being locally optimal along each trajectory, but then you discard that cost function and just have a stabilization cost inside the funnels. So you'd be locally stable if you're exactly on the trajectory, you're stabilizing to the trajectories. The cost I would incur from here is not the explicit MPC solution for a global feedback controller. It's trading feasibility for optimality, but I think in a healthy way, right? So an approximate optimal control. There are a lot of interesting details about how to implement that. Maybe one of the interesting ones I mentioned briefly when we talked about motion planning, but if you have a bunch of, so for smooth dynamical systems, we like to have smooth trajectories that execute and don't have discontinuous control actions, for instance. So for underactuated systems, trajectory optimization to an arbitrary point can be hard. So the way that we did the extend operation, if you will, you would pick a random point in space, write a trajectory optimization problem, which says at the end of, I'm going to parameterize a handful of, I could use direct collocation or whatever, I'm going to parameterize some trajectory, I'm going to search around in the parameters of that trajectory. The final value constraint, in RRT, you'd say, oh, there's a particular point on my tree I'm trying to get to. But I found it was very valuable to relax that and just say anywhere on this tree is that the distance between this final point and the tree should be 0. And then if you like, you could put derivative constraints to make sure you connect and stay along smoothly into the trajectory, okay? And you would see things like, so this would be, imagine we did it with a constraint, but you can imagine sort of like this distance function between that it says what's the shortest distance to the tree, if you will, and you say that distance should be 0, okay? And it's a nonlinear objective, but it did have important things like if I started to try to grow here, but then as it got closer, the dynamics prevented it from going here, it would eventually connect out here because that's what the dynamics were capable of doing. And that was much more important to get right in the LQR trees case than in the RRT case because the trajectories are much sparser, right? So in the RRT case, you would eventually sample arbitrarily close to the existing tree and be able to do a naive connection to get back. But in the, if I'm going to rejection sample everything that's within some neighborhood, right? This whole thing, I'll just rejection sample, then I'll never be arbitrarily close. And so I'd had to do much more work to connect nicely back to the trajectory, okay? The sums of squares certificates had, interesting objectives to sort of push out in the ways that would try to maximize the inlet of the funnel, stay inside the boundary. It often meant that you could be unstable for a while and stable again as long as you got into the boundary. Right, so there's lots of interesting details there. Yes, please.
How far have people managed to push this in, say, the number of dimensions?
In number of dimensions? I think the biggest, we definitely did quad rotors back in the day. The funnels themselves, we've done in 30-some dimensions. And that was, I think, solvers have gotten faster, our numerics have gotten better. So you wouldn't try to cover 30 dimensions. And that's actually a point I'm going to make in a second here. So this is I think, sort of a nice way to, so if you're like, if the blue region is small compared to the full state space, it could even be lower dimensional, right? The point I made about how I never visit most of the states that are available to me, right? I think you can target a smaller set of state space. So covering a very large dimensional space, bad idea, I think. but covering the relevant subset of a large dimensional space, each component does scale.
What does the relevant subset look like?
What, say it again?
What does the relevant subset look like? How do you characterize it?
The subsets of this is, so it depends whatever your parameterization of the Lyapunov function is. We often searched for time-varying quadratic forms, which is why we see a lot of ellipses here. And then they're just ellipses dragged through time. So that's what the image of the funnels look like. But there's nothing, you could choose to have quartic Lyapunov candidates, and you'd get funkier shapes. And all the stuff we talked about in the regions of attraction, you can still push out on the quartic with an ellipsoid, and all these things are still work here. So what does that look like, for instance? Oh, here's the, just sort of a solution, if you will, to the cart pole that had, stability from effectively all initial conditions. Whenever we turned the light on, it would not optimally, but approximately optimally return itself to the goal. And we got a lot of very robust control behaviors out of this algorithm on real systems. This is actually, I never finished saying what we did in total on the perching, but the final versions of the perching, I gotta get to the right part here. You know that we computed the nominal trajectories, we did local feedback, we did the funnels for this, but the way we got all the initial conditions we were interested in, and this is so what is it? It's a 7-dimensional space in our model, but then when we did it in 3D, it was higher, but it was a high enough dimension space that we wouldn't try to cover all of the initial conditions. We tried to cover all of the relevant initial conditions from what Joe did when he was throwing it off the, in the room, and we could cover this band of state space with more and more funnels that he computed that would all get to the perch. Okay, and that was how we got to the very robust behavior on the perching airplane. It was always Joe's, final goal was to just be able to throw it from, come on. And he got to the point where it basically always landed on the perch. Okay, the picture I think works well for walking too. So in walking, we have a nominal limit cycle. I alluded to the fact that you could do, the sums of squares trajectory, the verification along a limit cycle. This is the picture of it for the compass gate. You can compute the region of attraction in the orbital stability sense to the limit cycle. The hybrid version of that has to go through the jump, okay, and have a periodic Lyapunov function in the transverse coordinates in this case, so that they can line up with the reset maps, compute the region of attraction. And that's sort of a nominal controller. That's my steady state walking that I'm happy with. You could have many of them for different slopes or different nominal gates, if you will. And then to fill out the state space, you sample a new state that's, if it's outside, you find a trajectory optimization that goes back, and you can slowly fill out the state space with this approach too. And now, those extra trajectories, I think about those as sort of like recovery maneuvers, right? So I've got my controller every time. This is the most dynamic camera work Alex has had to do. Sorry for that. If I find myself in a weird position, then I have to find some recovery motion to get me back. But a relatively small library of recovery maneuvers can potentially cover a large portion of state space, and even eventually certify a large portion of the state space. Okay. There's nothing to prevent that idea from the feedback motion planning idea more generally even to work online. Okay, so imagine for a quadrotor, a standard idea for online planning with dynamic vehicles is to build a trajectory library, if you will. I've got like a fly straight maneuver, I've got a banked 10 degrees, a banked to the right, 10 degrees, and so on. And I build a tree of possible executions. Imagine doing that, and then along each of those executions, I could try to compute some notion of a stabilizing controller and a region of attraction or finite time certification of the performance there. And I build now a library of funnels. And then you put it down in a new obstacle course, and you can pick any of those funnels, and you can compose them as long as the output of one funnel lands in the input of the next funnel. Then off you go, and you've got a provably stable controller that can provably not crash with the trees, right? Assuming your perception system is perfect, which is not a great assumption. Building robustness in is super relevant and interesting. It's hard to do that rigorously. Okay, and there's there's ways. So you've thought about the Lyapunov stuff enough that I can sort of say quickly that you can imagine if you do have a region of attraction or a funnel along a trajectory that where V dot is going down for all states, and then every sub-level set. So if I verified it for V less than rho, I could even talk in symbols because you guys, I know I always use V and I always use rho, right? So V less than rho is my certification of my region of attraction. Then V less than rho minus a little bit is also an invariant set. And every sub-level set of my Lyapunov function is also certified to be an invariant set. So if my funnel from one motion was too big to fit in my funnel for the next motion, I can actually I can shrink it on the fly in order to make sure that they compose. And as long as I can find a path through the trees where the composition works and I'm in the initial conditions of the first funnel, then I have some sort of a certified controller that will get me through. Okay, so that cropping can happen aggressively. It can happen along the trajectories or whatever, but that's sort of the view is that you can chop sub-level sets down in order to avoid runtime constraints. There's also a lot of invariance. You can have like funnels that are parameterized by the location in space. Like an airplane has some cyclic coordinates. Where like if I have a funnel that works at x equals 0 and going this way, then it also works as x equals 2. I can just translate the whole funnel. That all works. So you can build these libraries and solve a relatively smaller problem of composing funnels in order to get a feedback controller that composes and grows through time. Okay, so this is, Ani worked super hard making that funnel appear in the real camera image. So props to Ani for that. That's a small RC glider in our motion capture setup. And he was demonstrating first that if I just design a simple trajectory with a funnel, I can actually execute it and stay inside the funnel. Empirically, even though the model of the RC plane was approximate, it was fit with system identification. He did some certification with some robustness assumptions about the parameters, and empirically he stayed inside the funnel. So that certification seemed valuable in practice. And then you could start saying, okay, let's do some virtual obstacles, right? Before we completely trust the system, let's just say the plane comes off the launcher, and not until the moment it's off the launcher does it suddenly hallucinate that there are some obstacles there that I have to avoid. So it has to make a decision in flight about which of the funnels it's going to execute in order to avoid the obstacles. That's what this version is. Okay, right there, hallucinate some obstacles and choose the bank maneuver or something like this. And by the end, Ani was able to make all sorts of obstacles, real obstacles, PVC pipes, in a motion capture arena. We didn't solve the perception problem in this part of the work. And he was flying highly dynamic trajectories with some notion of certification, if you will, of guarantees that you're not going to crash into the poles based on the sums of squares and feedback synthesis. Flying through a hoop. Flying through the obligatory MIT. Not our best MIT, but a little wonky. Okay, so that's kind of cool. So I want you to see that that's a general idea of feedback composition. The controllers could be, stochastic, robust. Output feedback, potentially. You have to think about if it's, you can certainly design an output feedback and certify it in state space. There's interesting other ideas to explore there, right? But I think that's a general notion. Now, the point that I think is hard to land, but I'll try, is just want to talk it through, is that I really somehow fundamentally think that the compositionality that happens here is important, right? Now this is not a theorem, this is philosophy, if you will, okay? But people talk a lot these days in learning theory, for instance, about combinatorial generalization. Maybe the most famous example these days is when people talk about natural language, that you've seen lots of sentences, you've trained on a big corpus of language, but you can assemble new sentences or understand new clauses that you've never seen before. They were never in the training set. But having trained on enough parts and having a suitable representation, you can often generalize to new combinations of words into novel sentences. Okay? How do you get that in control, right? I think feedback controllers are a natural choice for the sort of compositional elements, I think, of longer term, more complicated planning, maybe our cognitive architecture of control. Okay, so I said maybe legs feels a lot like feedback controllers, and booking a trip feels a lot like a plan, but nowadays I'm thinking a lot about manipulation, right? And I'll be honest, when I first started thinking about manipulation, I thought manipulation's got to be mostly planning, right? There's just so many different things you can do with your hands that doesn't it seem like you've never done, and like every time you're doing it, it's for the first time. Like even just loading the dishwasher, right? There's just so many different, if you look at the trajectories you take, like every trajectory is different. You're never doing the same thing twice. It's so interesting, actually, okay? But I've changed my tune almost completely. I don't think that scales. I actually think we have a relatively small library. Again, this is just philosophy, sorry. A relatively small library of controllers that are, can be adapted to some extent, goal conditioned, if you like, or you can use them in some operating range. And there's this core nugget of a skill, a feedback skill, or a feedback controller that can be then sequentially composed into much more complicated behaviors. If I had to bet, I think that high-level planning is important, but I also think that low-level feedback control's got to be important. And probably, as much as I love planning through contact, I think probably most of the things we do with our hands are probably leaning on controllers that are well-tuned and dialed in, and more like a feedback control. I think we have the ability in novel situations, like a Ninja Warrior course, or Josh Tenenbaum likes to show this ABC pickup game, where he challenged his daughter to walk up to a table, and there was just a bunch of random objects on the table, and he says, okay, pick one object with your right hand, pick another object with your left hand, and now using those objects, pick up this third object. So he's putting a human subject in the situation where they're trying to pick up a Kleenex box with a telephone and a light bulb. It's like, you've never done that before. That's a novel task. There's something about that you've just clearly not got an explicit an explicit representation for. And people are able, and sometimes it's a little funny to watch, but people are super good at finding these plans. So I do think we have the ability to reason about contact type behaviors. But most of the time, I think we're not doing that, right? Most of the time, I think we're composing relatively well-oiled feedback controllers, if you have to ask me. And I think this example, for me, was important because a lot of times robust control gets a rap about it being very conservative, right? That you can only do very, very conservative sort of motions, for instance, if you're trying to certify, give guarantees. And that was an example where I think even for very aggressive maneuvers, you can compose relatively aggressive maneuvers with the powerful tools from control theory. And I guess I'm highly optimistic about that future. Did I make that point at all? Yeah, does that make sense? It's still hazy for me, but I have to believe that that's important. Okay, I want to kind of put a bow around some of the things we've talked about. So, we started off, just to remember our journey here, right? We started off with very simple systems, model systems. They tended to be low dimensional, they tended to be smooth. We did the basics of dynamic programming. And optimal control. We had some beautiful solutions for that. We talked about Lyapunov theory, trajectory optimization, even policy search. What would it look like to search directly in the coefficients of the controller, right? And that got us through, I think, fairly interesting, smooth dynamical systems, model systems. And then we started to try to make them more interesting in sort of important ways that break the basic tools, right? So we did hybrid systems. A little walking robot here, right? Especially walking. And most of these tools had some sort of, with a little extra work, could handle these discontinuous, mixed, continuous, discrete systems, right? And we talked a bunch about planning and control through contact, which is my favorite instance of a hybrid dynamics. And then when things got more complex, so suddenly we had a whole humanoid, right, for instance, or an articulated arm moving through a complicated obstacle field, so now we had very high degree of freedom or complex obstacles. Constraints. Then we started talking about some of the reduced, simple models, for instance, like the centroidal dynamics, trying to make approximate models of a complex system in order to stabilize it for a humanoid. But we also started talking about weaker but more scalable tools for motion planning, for instance, sample-based motion planning. And then these last few lectures, we took our last big leap. Maybe it comes from from over here somewhere, but the other big way that we made things more interesting was, I'll draw my van der Pol oscillator, which was with all the particles moving around, right? Which was things got stochastic. And we started talking about or we start talking about stochastic and robust control. If we had observations and noisy observations, then we had to talk about output feedback. And we talked about today about feedback motion planning as a way to put a lot of these tools together. So that's a lot of coverage, right? This is, I mentioned at the beginning of the class, but almost every one of those topics I would love to spend a couple lectures on, maybe a whole course on, right? But I felt that it was useful to have one place where you'd at least see the connections between them. So that was a decision made to try to expose you at least to a lot of these ideas. I hope you see some connections and the like. So, what are the boundaries of what we, what's just beyond what these things can do? Like, what are some of the, what I think would be maybe the frontiers of dynamics and control, right? That's happening actively in research. It's still an extremely active area of growth. I'd say it's one of the best times ever to be working on this kind of stuff. Now, there's many answers to this. I'll give a biased opinion, partly intentionally, but partly myopically, like the things that I think about. But there's people that think a lot about, for instance, distributed control, multi-robots and stuff like that. And I just don't think about that as much, for instance. So, but in my world, I think there's so much we can do with this. There's so much to know in that space, and there's so much promise. But there are still some problems that I just think we don't have answers for in that whole world, right? So I think one of the big ones is the question of state representation that we talked about a bit in the output feedback. Or there's different ways to think about what that would mean. How do you build approximate models that don't have to capture every detail of the world? Sometimes I like when people call it intuitive physics, for instance, this notion that you could have very approximate, potentially wrong models of what's happening in the world, but they're good enough for control, right? I think that connects deeply with the ideas we talked about from output feedback. But I think we have to get past some of the hardness results, that we know that there's problems that are NP hard, and that for the entire class of problems as described, we're not going to find satisfying solutions, but people do it, and these are big questions. What's the state of my shirt? What's the state of the pasta, right? These are deep questions, right? I believe that. I think most of the things we've talked about here don't provide a satisfying answer to how do you do control from cameras. And that sounds like a narrow thing to say on a big frontier, but I actually think it's pretty fundamental, and it mixes up with the state representation question, of course. But I think a lot of the great things that have been happening recently, as computer vision went through its revolution, was that we now think we can close feedback loops through camera signals, okay? And there's a lot of things that people are having success with now, but I don't think we've gotten to the core of that idea yet, of like, what's the right way, maybe what's the right representation, what's the right way to get from an RGB image into something that I can reason about in a modeling sense, in a planning sense, in a feedback control sense. And they're just such an important sensor, right? that I think we're gonna see revolutions, I think, in our understanding of what's the right way to do control from cameras. And one of the reasons that's such a big deal is that once you have a camera, you expose yourself to like the diversity of the world. It's not a cart pole on a track where the state is 4 variables. It's suddenly like I'm driving through San Francisco, and you know, anything can happen. And so you think about robust control. You know, we're going to prove that, you know, this thing's going to work in all cases, for instance. How do you do robust control in downtown San Francisco, right? This is a hard question. And one possible answer is, do we need to make right distributions, you know, over, you know, or somehow certify robustness, or reason about robustness in a worst case sense, in a approximate sense, you know, over open worlds, open domains. That's what people are calling it, right? Where like the open world video games are the ones where you can just go off into places that the designers never intended, right? And how do you write W is drawn from San Francisco? I don't know how to write W is drawn from anything that can happen in San Francisco. And I don't know how accurately we need to write down that distribution, right? I think there's a sense which for easy, you know, when you have lots of control authority, you can be pretty sloppy with your uncertainty set. And there's a sense where to be really good, you'd have to be, you know, detailed with your uncertainty set. But I don't know, to achieve the promise of robotics, how dialed in we need to be to the distributions of the world. That's a big, big question for me. You know, I don't know if we have to like build the matrix in order to have certified control. Of course, I've said over and over again, I'm extremely excited about the, you know, machine learning plus control coming together, both in the empirical sense and in the theory sense, right? I think this has generated sort of new problem formulations, brought new mathematical tools, and just a bunch of smart, excited, energetic people into the field. I think it's really a super interesting and exciting area. And I think, you know, connecting data, for instance, to control, which is somehow related to a couple of these above, but I think it's very, very interesting. I think the controls view of the world has tended to say, you know, I want an algorithm that works like for all A matrices, right? And, you know, A, B, C, and D, right? Like I must have an algorithm that for any A, B, C, and D, I can tell you what works and what doesn't work. And some of the hardness results really do come from this fact that that's a very large class of possible systems. And if you were to somehow restrict your reasoning to algorithms that just had to work in problem instances that were dialed up by, you know, Mother Earth, right? Or you know, the things that a robot's actually going to experience, then maybe the robot is never going to experience some of the squirrely cases that are giving us NP hardness challenges, right? So do you have to get that from data? Do you get that from distributions? But these are big questions. I'm super excited actually about what happens when big data comes to controls. I don't think it's really happened yet. Everybody else has big data. I'm kind of jealous. I think it's starting to come, right? Like, so I think there's, for instance, people talk now about fleet learning for robotics, right? If I don't have one robot that needs to design one controller to operate in all situations, but I have an entire warehouse of robots, and I've got a warehouse in every city in the country, and they're all doing some similar things, does that fundamentally change the way I should design my controllers? And how should I share knowledge? How do I adapt to different distributions and the like? really good, exciting questions at the edge of this. You know, what happens when big data comes to control? That's my short list right now. You know, ask me again in a year, maybe it'll be different. But I guarantee it's going to be different. Things are moving so fast. Things are so exciting. There's really never been a better time to be in robotics and control and learning. So I hope that that coverage gave you some exposure. I hope you it whet your appetite. I hope you love dynamics a little bit. And go off and change the board for next year. Do great things. I will see you on Tuesday. It's your turn next. And we're happy to keep answering questions about projects. All right.